Good evening. It's wonderful to see this audience assembled today at new venue for this quite unique event where we have Dr. Venki Ramakrishnan with us. You heard an introduction to Dr. Ramakrishnan. I'm Somak Raychaudhury. And of course, the occasion of this event is this book that Dr. Ramakrishnan has written over the last year called Why We Die, The New Science of Aging and the Quest for Immortality. This book has been on my side of the bed for a while. I was gearing up to reading it for a long time, and my wife kept taunting me, saying, "You seem to have a block against starting to read it. It's such a grim title." Of course, the subtitle is far more positive. But when I started reading it, I finished it in a day. And that is because, if you have already read the book, you know, it tackles a very, very important topic that all of us are interested in, but know very little about. And it's also a topic for which research has happened in a very accelerated way over the last few decades. And so today we're going to talk about that, a lot of what is in the book. And of course, we'll throw up questions at the end. But I thought I'd also talk about how this book relates to Dr. Ramakrishnan's original work, which, of course, was, as you know, it led to the Nobel Prize in discovering and describing the structure and function of the ribosome, which, as you know, our biological system depends on the DNA, and to take the information from the DNA in order to make protein synthesis, which is the basis of parts of our being, of our body. The ribosome plays a very, very important role. But I mean, we'll get there. We'll also, Dr. Ramakrishnan's first book was based on his discoveries and work on the ribosome. But this book is pretty different. And I thought I'd first start by talking about, what attracted you to actually write this book. Does it directly come from your research on your life's work? And also, does it also then see this in a much larger socio-political or philosophical perspective?
So my own work is peripherally related to it, in the sense that the body's ability to make proteins and make them in the right amount and at the right time, and get rid of them at the appropriate time, all of that is very closely related to the aging process. And there are many people in my field who do work on aging. And there's one person in my lab who works in a field very related, in an area very related to aging. But by and large, my own work doesn't directly revolve around aging, but it's very close to the field. So why did I write this book? Well, there are lots of reasons. One is it's a long-standing existential question. We have wondered about why we age and why we die and lifespan and so on ever since we were humans. But it's only in the last 50 years or so that biology has come up with some answers for why it happens the way it does. And this means that for the first time, the tools, the knowledge we've gained and the tools we've developed may allow us to tackle aging. And that in turn has led to a rather big growth in the aging research or anti-aging establishment and industry. And there are some reasons for that, and that is societies are getting older. People are living longer, fertility rates are going down. Even in India, there are only 5 states that contribute to this overall fertility rate of India. The rest of India is below replacement rate. And so what this means is that societies are getting older, they're being replaced more slowly, so you have an increasingly aging population. And there's a real need to keep this population healthy in old age. And that's driving a lot of research. There are also some of the more optimistic end of people, or shall I say, more of the cowboy end of the spectrum, who want to postpone death altogether. They want to postpone it either indefinitely or for a very long time. And this is also driving a lot of what I would call charlatans and dubious practices in the field. So I thought I would take a hard look as somebody who doesn't have a vested interest. I don't have a company that works on aging. I'm not selling you a product or a pill. I'm not selling you a service or even selling you advice, except I'm selling you a book. And so I thought I could afford to be very pragmatic and objective, as much as anybody can be objective.
Because we talk about the cryonics angle later. I mean, there are fascinating parts of the book that are very different, look at very different ways of looking at aging and death. But let's start from the end of the book. And the end of the book deals with the sociological and philosophical aspects of death and aging. And I find it very fascinating to look at, and the way you have also pointed out, how different cultures, due to their religious background or socio-cultural background, deal with aging and death differently. There are cultures in which older people are revered, or at least there's a myth of revering older people in India, whereas many other cultures do not do so in the same way. There is a structure in the tradition of many Indian cultures of how people should wind down different activities and prepare for death traditionally. Then there is a question of how to look after this rapidly aging population. If you look at the US, the boomer population, they're all now aging very very rapidly, are in the range where they have to be looked after.
And not very gracefully.
And not very gracefully at all. Whereas India is kind of a few decades behind that, I think, and still the population is. So how do people in these different cultures deal with older people differently, aging people differently?
I may be a bit cynical, but I think all cultures are basically death denial cults. For example, the philosopher Stephen Cave says there are 4 ways in which humans have tried to deny or be delusional about death. One is the idea that, well, your body is simply going to be resurrected at some point. And so the Abrahamic religions, which are Judaism, Christianity, and Islam, believe that the body itself will arise on some judgment day. And that's why those religions traditionally insist on burial and not on cremation. Then you have the Eastern religions, which say, well, the body may disintegrate and it may just disappear, but you have an immortal soul which will go from that body to some other body and keep on doing this until it somehow finds some eternal salvation. And then there's another idea, which is that, well, even if none of these things are true, we can remain immortal through our works. For example, if you write a great piece of literature or music, or you've made a great discovery, then your name will live on even after you've died. Or if you don't have that ability, but you're very rich, you can endow a foundation or a building, and that'll be named after you. And that's another way, kind of immortality. And another idea, of course, is that you can live on through your offspring, because they, in a sense, carry some elements of you in your part of your genes live on inside your offspring. But of course, all these other ways are not really ways of avoiding death. So plan A is simply not to die. And that's what most people aspire to. And even in India, nobody really wants to die. I mean, they may be they may pretend to be philosophical about it, but if you ask somebody, do you want to die next week? Most of you are going to say no. You'd rather not, even if you're very old, you don't want to die next week. Maybe some indefinite time in the future.
But then let's look at the specific problem of that. I mean, let's not talk about metaphorical notions of mortality. You said in this book in one point that, of course, animals can sense death, many animals. However, most animals, non-human animals, cannot really have a sense of mortality, but humans do. We are unique in that. And we want to live longer. But why should we live longer? I mean, does society gain from people in general living longer? I mean,
No, it's not to do with society. It's the fact that we have evolved, all animals have evolved to avoid danger. And animals may not know about death, that danger leads to death. They may not have a concept of mortality. At least there's no evidence. They know if a member of their herd has died. That we have evidence for. But we know about mortality. So when we think of mortality as a cessation of existence. It means we stop existing, and we don't want that. And perhaps that's a deep-rooted behavior, that fear of death, because if you didn't fear death, you would be at an evolutionary disadvantage. You would do all sorts of risky things and die prematurely before you had a chance to reproduce. So I think a fear of death is probably deeply ingrained as part of our biology.
But I mean, if you look at creativity and as that manifests itself as you age, there's a famous book by Subramaniam Chandrasekhar, who, like you, is an Indian origin Nobel laureate, who wrote a book called Patterns of Creativity, where he made this very strong statement that in the sciences, people do their work very early on, major work, whereas in the arts and humanities and creative arts, people actually produce some of the best work later in life. And you refer to in the book to something that I think Ishiguro said in one of the literary festivals, which seems to indicate people actually do a lot of their work when they're very, very young. And so what's the use of having humans live to 120 if really it doesn't push the boundaries of creativity?
But that's you're asking evolution to do something useful. That's not how evolution works. Evolution simply doesn't care about anything other than whether your genes are passed on successfully or not, because the selection operates at the genetic level through the number of your offspring. Yeah. And so the question of whether it's useful or not is not relevant to biology. We may like that because we have evolved brains and we've evolved a sense of consciousness and awareness and so on.
I think most of the book is, of course, dominated, though I started from the sociological aspect of it. Most of the book is dominated, of course, by your work dealing with the biology of aging, and in particular, the work on how cells repair themselves, how proteins repair themselves. Could you tell us a little bit about how the connection worked from your early work on ribosomes and how that got you into
So as I said, only one aspect of aging, which involves how proteins are regulated, is related to my work. But aging has a wide range of causes, from damage and changes to our DNA, to the shortening of our chromosomes, to this repertoire of proteins that we make at different rates as we go along, and then to organelles in our cells called mitochondria, right, which are descendants of bacteria that an ancestral cell of ours swallowed up about 2 billion years ago. And since then, the ancestral cell and the mitochondrion have co-evolved in a symbiotic relationship. But the mitochondrion is an extremely important compartment in the cell now. It's where we oxidize carbohydrates like sugar into useful chemicals, and that's where oxygen is used to essentially burn the sugar. And so when mitochondria are damaged or dysfunctional, it has an amplified effect on the rest of the cell, and it's a major cause of aging. Another cause of aging is that cells reach a state called senescence in response to stress or DNA damage. And these senescent cells are dysfunctional. They don't behave like normal cells, they don't divide, and they secrete inflammatory molecules. The inflammatory molecules themselves can go on to damage other cells and increase senescence. So it's a kind of self-perpetuating autocatalytic process. And so as we age, we accumulate senescent cells causing systemic inflammation, and that's another big cause of aging. There are cells in us that are called stem cells. These cells are responsible for regenerating many of the tissues, in fact, all of the tissues that make up our body. And as you know, our tissues are constantly replaced. There's a saying that essentially all of you is replaced about every 7 years because they're not completely uniform. For example, brain cells only get replaced rarely or very slowly. But the point is that as we get older, these stem cells also decline, partly due to them. They also become senescent. And so if they decline, your ability to regenerate tissue, even to regenerate cells of the immune system, declines. And then your immune system declines, then you have problems with cell-cell communication. So you can see that every level, from the very molecular level like DNA and protein, all the way to cells and tissues, there are processes that decline with age. And when this leads to a critical loss of function, then the individual, the organism, can no longer function as a coherent whole. Remember, when we talk about death, we're talking about a particular kind of death. So when you're alive, millions of cells in you are constantly dying all the time, but you don't even notice it. That's just part of life.
And when you're dead, there are a lot of cells that are still alive,
fact,
right?
When you're dead, most of your cells are still alive at the point of death. Eventually, they quickly die off. But at the point of death, most of your cells are still alive. In fact, entire organs are still alive, and you can donate your organs to someone. Yeah. So what we mean by death is this loss of ability to function as a coherent individual. And so that's what breaks down as a result of aging reaching some critical point.
I find it, I'm an astrophysicist, so I gave up biology pretty early on in my career, and I'm sure there are a lot of people in the audience who also did so. So reading your book, there were some really astonishing numbers, figures that got my attention in this context. And if you look at not organs failing, but individual cells dying and the number of cells that die. Of course, one of the major things is you at one point out the work of Thomas Lindahl, who later got the Nobel Prize, talking about the C to U, the cytosine to uracil, DNA to DNA cytosine being destroyed. And the staggering number that you put there is that even in the presence of water, which is something that's there everywhere in our body, about 10,000 of these can degenerate in a single day. You talk about the damage inflicted to DNA of the order of 100,000, a lakh every day. These are immense numbers. And on the other hand, there's a system in the body to replenish all of it.
Yeah, and actually that's a very important point. Until, a few decades ago, aging was not considered a very fashionable field to work on. In fact, mainstream molecular biologists viewed the field with some disdain. They said, well, it's just wear and tear and entropy. What's there to study in aging? But the reality is that if we didn't have repair mechanisms and regeneration mechanisms, we would disintegrate very quickly. And it explains also why lifespan is very different in different species. Yes. For example, if you take something like an insect, it only lives for about a day. There are some insects which only live for about a day, others live for a few weeks. And then at the other end, you have animals that live for several hundred years. So if it was simply wear and tear and entropy, we're all made of the same material. Why aren't we all dying aging at about the same rate? And it's because of natural selection. Evolution doesn't select for longevity. Evolution selects for fitness, which is the ability to pass on your genes. And each organism has a limited amount of resources, and all these repair mechanisms and regeneration mechanisms take up resources and material and energy. So if you have a limited amount and you spend it all on that, then it may or may not be advantageous. For example, if you're a mouse, there's no point in a mouse evolving to live to be 40 or 50 years, because long before that, it will have died off it would have been killed by a predator or killed in a drought or a flood or of starvation. And so in the mouse, evolution has selected for putting those resources to rapid growth and maturation. So a mouse matures very fast, reproduces quite well, and rapidly passes on its genes before it dies off, presumably due to external causes, typically in the wild. And so if you take larger animals, the equation's different. There, it is advantageous to have a slower metabolism, longer lifespan, more time to find a mate and nurture offspring and so on. So evolution explains these disparities reasonably well. There are outliers which sometimes are a puzzle, sometimes they're just a particular environmental reason. For example, bats, which are the same size as mice, live 20 times as long. So there are bats which can live for 40 years. Now, why is that? Well, bats can fly around, so they can escape predation much more easily, and they can also forage over a wide area, so they're less likely to starve to death. And so you see bats living much longer for that reason. And it also means that evolution will choose traits that are advantageous earlier. For example, these growth pathways are advantageous early in life, but they're also disadvantageous later in life, because those same pathways are responsible for processes of aging. So evolution does not care how long you live, cares about fitness, and the result is many things that help us early in life, sometimes by preventing cancer early or helping you grow fast and mature early, cause you to age later in life.
In this context, I mean, another fascinating number I came across was very, very interesting. I mean, I just wanted to say that at Ashoka
It's because
University,
you're an astrophysicist, you're very interested in numbers.
Numbers, that comes through. At my university at Ashoka, I teach a course in the first year together with a friend of yours, Shashidhara, who's now the director of NCBS, called Time, in which I talk about the physical aspects of time, relativity, entropy, the arrow of time. But Shashi teaches circadian rhythm and also how animals keep their rhythm. And in your book, you talk about how it seems that in major organisms, everybody has the same total number of heartbeats in their entire life, about 1.5 billion. That's an interesting number. So, for example, a turtle who lives many hundred years would have a heartbeat every 10 seconds, and the mouse would have a... And then, with the great joke that you have in the book, which says maybe it's the same number also of revolutions of a car engine. What's so magical about 1.5 billion?
I think the number of heartbeats in mammals being roughly constant, that is an observation. It's because smaller animals have a faster metabolism, and the reason is heat loss is proportional to area, but their area to volume ratio is much larger than a larger animal. It's simply one goes as r square, another goes as r cubed. So if you're larger, you have a lower area to volume ratio. And so smaller animals, because they have higher heat loss, they also have to have a faster metabolism, and they also need, therefore, more food in relationship to their mass. And as a result, their hearts beat faster. And even in humans, a child has a higher heartbeat than an adult. And so that's just one of those observations. It's just peculiar that it seems to be roughly constant, although, as I said, there are always some outliers.
No, but also, these numbers often tell you something that's underlying, which may be...
Well, the underlying thing is the metabolism.
Of course, yes.
Metabolism is roughly related to size, and it's inversely related to lifespan. The higher the metabolism, typically the lower the lifespan.
The other point, I think, which I thought was very, very interesting in again, that same chapter, was you talked about how very early on people realized how onset of cancer can be very important in humans. And so discovery in the early 20th century on how chimney sweep boys had cancer of the scrotum. Later on, people realized coal tar or even X-rays can cause and accelerate cancer. On the other hand, we also know that there are mechanisms within the body for children, for example, that prevents cancerous activity. And so as you age, you get more cancer. But there are larger animals like elephants and whales, which have some mechanism of not getting cancer.
Yeah, so even the cancer mechanism we have, the mechanism is that it senses DNA damage or some sort of damage to the cell, and it sends it into senescence, which is this state I told you where things don't divide and it secretes inflammatory molecules. And the reason you do that is early in life you don't want a cell with DNA damage to hang around because it could become cancerous, and that could destroy the entire organism. Whereas if you simply destroy that cell, well, that cell is 1 in a trillion or so, so you don't notice it. And so the mechanism has evolved to do that. But that same mechanism then causes you to age later by producing senescent cells at an increasing frequency later. So you can see again how a cancer mechanism early in life, which prevents cancer early in life, can cause you to age later in life. Now, if you take a large animal, the chances that one of their cells would become cancerous is much higher because an elephant has many more cells than a mouse. Yeah. And yet, the elephant gets cancer at a much lower rate than a mouse. A mouse is much more prone to cancer, fairly early in life. And so, what's going on? Well, it turns out that these repair mechanisms that repair the damage to DNA there are many more copies. For example, there's a protein called P53 which plays a central role in the DNA damage response. And there are many more copies of that in an elephant, 20 copies as opposed to 2 copies in a mouse. So you can see how evolution has sort of made it possible to grow large and yet not get cancer.
So is there then a lot to learn from nature and other animals? I mean, if our basic constitution is such that an elephant has so many of these built in, it probably evolution did that. But do you think that people who are now looking at ways of prolonging life, like the cryonics people, the rich people in California.
I think, would they DNA damage and the DNA damage response may be a cause of aging, but it's also deeply implicated in cancer. And all of the therapeutics that involve that have been directed at anti-cancer therapy. There hasn't been much application of the DNA damage and DNA damage response field to aging as such. That could change. And as far as having multiple copies of this protein, I think that's very far-fetched because it would involve cloning these genes into humans, and I don't think that's going to happen anytime soon.
But aging doesn't only depend on cellular failure or protein failure. It's actually organs. Individual organs can age in different ways. Individual organs fail at different times. And when we're looking at living longer, living to be 100, 120, 150 or whatever, I wouldn't want to live to 150 if my organs don't work, if I have no brain function, so of course the organs have to work together, right? And it's the interaction between the organs that keeps us alive. How does one design a human system to live longer with the organs working together?
You're right in that aging has these multiple causes, and things have to work in a coordinated way. But there is a fundamental hierarchy. I think it all starts at the molecular level and then goes up to collections of molecules and then to components of cells and then the cells themselves and then tissues and organs. And it is somewhat striking that even interfering with very specific causes of aging, like interfering with a pathway that's involved in aging, or, for example, reprogramming cells so they have more stem-like character for a while. Those things seem to be, or getting rid of senescent cells, they seem to have a global effect in animals. So they are doing something to make older animals seem like younger animals by various criteria, by various biomarkers, and also simply by visual characteristics, the ability to move and the quality of their skin and fur and eyesight and so on. So there is something going on where if you tackle one important cause of aging, it seems to have an effect on other aspects of aging. Now, how much that will hold up over the long run isn't clear, and we still have to. A lot of these experiments are done in mice for obvious reasons, because mice don't live very long, so you can do the experiment fast, and also they're well-established laboratory animals. But the translating that into human biology and making it safe and efficacious for humans is going to be a challenging area.
Another aspect of the cryonics people who have lots of money and want to prolong their lives are deep into the technology of trying to make bodies sleep and then be woken up again. And of course, an astronomer like me would be very interested in that, because if I want to do interplanetary travel, I would like to take astronauts and put them into sleep and then wake them up again. Is there any sense?
I don't know if you've seen the movie 2001, but that's essentially they were put into some deep sleep, and the hope was that they would wake up.
Do you think that's ever going to happen? I mean, is there a cellular way of doing this?
There is absolutely no evidence that cryonics works on humans. It hasn't even been shown to work on a small animal like a mouse. We can freeze small biological entities. For example, we can freeze cells, many different types of cells, and thaw them up later, and the cells are still alive. It's not clear that it's 100%, but it's reasonable. So biologists routinely freeze cells. They can even freeze embryos. So human embryos or animal embryos in research can often be frozen for later use. But once you get beyond a certain size, freezing becomes very problematic. And the reason is that water, when it freezes, expands and forms ice, and that then destroys all of the surrounding tissue around it. I mean, all our cells and our tissues are filled with water. They're about 80% water. And so anyone who's frozen fruit, for example, or vegetables, you know, if you just freeze it and thaw it out, it's not going to look the same, or you're not going to get fresh strawberries after you freeze it. So there is a legitimate field of biology called cryogenics, which is trying to invent better and better ways of freezing biological samples. But no one has even frozen a small animal like a mouse and restored it to life. So the idea that you can take a human, and by the way, to do this to a human being, you have to replace their blood and all their lymphatic fluid with some antifreeze, like ethylene glycol, or I don't know exactly what the substance they use is. It's something that won't form ice when frozen. This, of course, kills off the person. Of course, the person is dead anyway, but when you freeze them, there's really, I don't see any way that they're going to come back alive. And indeed, the companies that do this don't actually promise that they're going to make you come back alive. They simply say, we will freeze your body according to this protocol, and we will keep it in liquid nitrogen indefinitely, and you have to pay $200,000 or something. And there are enough rich people for whom $200,000 is nothing. You know, they won't even notice it. So they figure, well, there's maybe a very small chance it'll work, but what if it does? So I'm in, and the 200,000 I don't care about. So a number of, so they capitalize on these rich people's ego and desire for immortality, and that's how these companies survive.
Any discussion on death is bound to veer towards the morbid and bizarre. And so what I'm going to do now is kind of round up this conversation and see whether people in the audience have questions to ask you. The last thing I would like to ask is, which is probably not discussed as much in your book, but is bound to come to the mind of people who read the book. We are thinking of prolonging lives, we're thinking of living longer. On the other hand, around us, we see the environment breaking down. The future of our surroundings seems pretty bleak. Only the other day we heard of Donald Trump pulling out of the Paris Agreement, and there's a lot of movement from various leading countries not really paying attention to the environment. So how does one balance the fact that we want to live longer, but the world that we want to live longer in is progressively being destroyed? What is your take on it?
Well, there are two different things. One operates at the social and global level, and the other operates at a personal level. So no matter, as I said, the desire to live is deeply ingrained. And there's an old joke, which is, who would want to live to be 100? And the answer is somebody who's 99. And yes. Of course, if somebody came to you tomorrow and said, look, modern biology has produced a pill that's going to give you 10 years of extra healthy life. I don't mean decrepit life, but healthy life. Most people would take it. In fact, I'm on two classes of anti-aging medicines myself right now. I'm taking statins for my cholesterol, and I'm taking blood pressure medicines for my high blood pressure. And although they're not technically speaking anti-aging, their result is to keep me healthy and potentially live longer. So I think this is an individual thing. And the difference between, well, firstly, if we live longer, it doesn't mean that we're going to be overpopulated. Japan has dramatic increases in life expectancy, and Korea, and yet their population is actually declining because fertility rates are dropping even faster. So it's not a given that just because you live longer, we will have overpopulation. You might transiently, but in the end, you might not. But the separate thing is, what's good for us as individuals, the choices we make as individuals, aren't always, what shall we say, in agreement or concordant with what's good for society or the planet. And I'll give you an example. Everybody in India knows that cities in India, 83 of the most 100 polluted cities in the world are in India, okay, including the top few. They've long over. So if there's one thing India's, world beating, it's in having polluted cities, and we all know that it would make much more sense for society to create cities where people can walk, bicycle, take mass transit, etc. But instead, as individuals, we see the problem and we solve it at an individual level by getting a car as soon as we can afford it, so that we don't have to deal with the traffic, etc., and we can isolate ourselves. So this is just an example of how individual choices are not necessarily what's good for society.
Well, thank you very much. Thank you for this wonderful conversation. Just before we end, I'd want to thank you very much. I'd like to see whether anybody has mics that can travel to people who have questions. And I'm not sure how many. 2 questions? Okay. You can choose who to take the mic to. Can you please introduce yourself, tell your name, and then...
Hello.
And keep the question brief, okay?
Yeah, my name is Debabrata Sur. I'd like to ask about Sunita Williams, who is in ISS for a long time, and she's experiencing zero gravity for a long time. How the cells are affecting in her case?
I'm not an expert on the consequence of zero gravity, but I do know that long periods of zero gravity have lots of consequences. For example, loss of bone mass and other physiological changes. So it's probably not great for aging. We have not evolved to be in zero gravity environments. And this is something for, if you're doing very long-term space travel, there's all these plans to go to Mars and hopefully return, that they're going to have to create a gravity environment somehow in these spaceships, I think.
I suppose the answer is it's not known. I think with these experiments we will know.
I'm Shiv Shankar Palit. I'm a chemistry person essentially, sir. Do you think there is any hope, like understanding the biochemistry of extreme organisms or extremophiles as they call it, and extrapolate it to how humans can live longer maybe, because there are very less known.
Extremophiles don't live longer. For example, many of extremosophiles are bacteria.
Yes.
Or archaea. So their aging is not directly relevant. There'll be some things in common.
Yes.
I mean, all species encounter DNA damage and things like that, but it's not clear how you would directly learn from them to apply to ourselves. And the fact that they're extremophiles is a different kind of evolutionary adaptation that doesn't have directly to do with aging.
Okay. Thank you, sir.
Thank you very much. And I think I'm told that we have run out of time. I'm sorry we can't take any more questions.